Hey there, Calc 3 folks, back here with another video in our series of videos coming from Chapter 14 material. And I should be careful there. I'm trying not to reference little items like that because it's going to change over the semester. So if you're watching this years from now, it's probably no longer Chapter 14. Who knows what it is. But what we want to talk about today... we want to go a little further with vector valued functions. We kind of got into the analysis yesterday, last class. We've looked at introducing vector valued functions, and I've actually already started to post some of the a video on limits for vector valued functions, applying limits to these functional values. What we are going to look at today is going a little further with that and using the limit to develop a definition for derivative of a vector valued function. And with a definition of the derivative, we can then develop the understanding of an antiderivative for a vector valued function. All right? And that would be in the next video down the line. But I want to show you, get into a little bit today on derivative of vector valued functions, and at least get you started with them. There are some other properties and rules that I'm not going to get into in this video that do appear in the book, derivative rules. They do exist and you can apply them. Just take note. But I don't think we're going to encounter too much of it in our work there, folks. But take note, they're there. I'm not going to, spend this video on that. I'm going to try to keep this video brief and get you what you need. Right? So, to begin with, let me bring this over to you here, folks. We are looking at derivatives of vector valued functions, and the idea of a derivative is not a new idea to us. It is an idea that comes from calculus. It is an idea that is was one of the first applications of our understanding of the idea of a limit, and that is what calculus is. Calculus is the study of limits. So, this idea of a limit is with us in the concept of the derivative, and we saw this limit develop into the derivative through the definition of the derivative, and that's what I have up here to begin with, just to kind of help us recall what we currently have in terms of an understanding, right? We understand from the definition for a derivative presented back in Calc 1, given some function y equals f of x, the derivative of f at x, denoted by y prime or f prime of x, is equal to a limit where the index in the limit is the value of h, and h is going to be heading to a smaller and smaller value approaching 0. And the argument of our limit is prepared by taking f of x plus h, subtracting from it f of x, and dividing that entire quantity by the value of h here. Right? This was how we defined the derivative back in Calc 1. All right? And recall that many of our rules for, did I write integration? What was I thinking? Differentiation, right? Were developed from this definition, folks. If you had a good calc class, you probably got into at least proving a few of the rules with this definition, right? Well, this definition is going to come back in an analogous situation where we look at the case for vector valued functions, right? And it's going to come back in the context of vectors, right? So that's what I make note of here. For vector valued functions, a very similar definition is given, but within the context. I probably didn't spell check this beforehand. I always spell check them before I publish them. But see if you can spot the spelling errors. That it might be a good game to play while I deliver these to you. So here's our definition. All right, given r bar at t, given some vector valued function, right, at t in r sub n, right. Given r bar at t, like I said, my grammar is not always the best. Vector valued function at t, right? In n-dimensional space, the derivative of that vector value, r bar, at t, is given by a very similar looking defined value. If we page up and compare it to what's above here, we do note that we have the notation r bar of t's derivative indicated with the prime notation, that is r bar prime of t. You could also incorporate into that the Leibniz notation and consider taking the derivative with respect to t for r bar of t. All right, you might see that also as a highlighter for derivative, and you could even take that further and maybe look at something like dr bar of dt, like such, in the Leibniz notation. All of these are different ways of denoting the derivative of a vector valued function given by r bar of t. Now, how do we define these items, or how do we define this item, right, this idea? It is defined by what we have here on the right hand side, where we have essentially the statement given above here, right, where instead of using the scalar valued function little f, we are using the vector valued function little r bar of t, right? And we are just looking at r bar of t plus h minus r bar of t and dividing that by h in our understanding of the derivative of a vector valued function. All right. Now, if you recall, that definition brings up about a bunch of rules if we want to develop rules. But the way we're going to approach it is we are going to apply it in general to a vector valued function that exists in some n-dimensional space, and kind of observe the result in a generic situation to understand how this operation operates, right? So, as for applying the derivative operator to some vector valued function, the definition can be applied to the generic formation of r bar of t in some n-dimensional space to observe this result. And that's what I do here in the notes. And I considered, to begin with, a vector valued function in two-dimensional space, r bar of t equal to x of t comma y of t in 2 dimensions. Applying the derivative operator to r bar, in this case, yields the following result, right? By definition, r bar prime of t, the derivative, is given by the statement on the right-hand side in the definition, where in general here, since r bar of t is equal to x of t comma y of t, r bar of t plus h is then going to be the vector given by x of t plus h comma y of t plus h for the components. And if we substitute all that into our calculation for r bar of t, right? If we substitute in for r bar of t plus h this quantity right here, we prepare this item. And if we substitute in for r bar of t this quantity right here, we prepare this item, right? And the argument of this limit presents itself as we see here, where this is nothing more than a little vector operation, folks. This is this vector minus this vector divided by a scalar constant, little h, where we can simplify this into what we might think of as a simpler vector statement. First of all, we can certainly take the difference of these two vectors, and if we do that, we will prepare the following, right? Where if we then take that difference and divide by h, we can say that what we have here in a sense is going to be the limit of this component minus this component divided by h for the first component. And for our second component here, we can see that that is the second component here minus the second component here, all divided by h. Where what we really are doing in this limit calculation above is applying the limit to this vector in its form, right, seen here. Where what do we know about the limit from the previous video or set of notes is the limit operator will just distribute itself across the components. It'll distribute it to this first and second component. So if we apply those ideas and distribute the limit across those components, right, we prepare these two arguments inside of the vector using a limit. Now take a moment to look at this, and take a moment to look at this, and they should look familiar. They are not a limit of a vector-valued function, though. If you notice, right, these are scalar-valued functions used inside these arguments. Where have we seen scalar-valued functions used? In this format. Well, if we scroll back up, that's what we've seen above up here for our understanding from Calculus 1. F is a scalar value function, just like what we see down here for function x and function y that make up the scalar functional descriptions of our components in the vector valued function. All right? So what does this mean? Well, from above, we can say then from this must be all just x prime of t. All right? Because what were we able to say about all this? This was just f prime of x. Well, x has been replaced with t, and function f has been replaced with x. So this is really just x prime of t. And we see something similar for y. Let me not go too far. And we can bring that result up into view, right? What this implies here is that really what we have then is this two-component vector given by the derivatives of the individual components. And we actually bring that together in a conclusion here, folks, right? Thus, given r bar of t equal to x of t comma y of t, the derivative of that vector valued function is just the derivative of the components of that vector valued function, x prime of t and y prime of t respectively. Right? Indicating that the derivative operator, just like the limit operator, will distribute itself across the components. And it's a rather intuitive process. Right? An application, a rather intuitive application of the derivative operator to a vector valued function. Excuse me. Similarly, if we look at this all in three-dimensional space, right, and we add a component to our vector valued function in 3 dimensions, well, the derivative operator will also just distribute itself to that third component, and its derivative will be given by x prime of t, y prime of t, and z prime of t. Z of t being that third scalar value function describing displacement in that third direction of space when thinking about three-dimensional space. All right? The derivative operator distributes itself across the components of the vector, right? In any n-dimensional space, folks. All right? So let's look at an example. All right? Here's a vector valued function. Consider finding r bar of t for this vector valued function given here. R bar of t equal to the cosine of t squared, comma, t times e to the t, comma, t squared plus 3t minus 6. How's the vector valued function going to behave? Well, how's the derivative of the vector valued function going to behave? Well, it's just going to distribute itself across those components. You can see here I make use of some, I believe, the other notation here, right? We might take note that r bar prime of t is just the derivative with respect to t applied to r bar of t. Let me fix that, all right? Which means this derivative operator is just going to distribute itself across the 3 components of this 3-dimensional vector valued function. All right? So in the end, what we're really going to be looking for are just derivatives as we have calculated them way back in the days of Calc 1. We're just going to follow our derivative rules that we learned back in Chapter 3 of calculus, right? Back in that study of the derivative in calculus. All right? So what's the derivative of cosine t squared? How do we find that? Well, if you think back, that's a little chain rule because we're looking at a composition of 2 simpler functions, right? Where from chain rule, the derivative of the interior function t squared is negative 2 t, which is, well, is 2t, which is brought out in front as a constant multiple. And then the derivative of cosine for our interior, where we often think of that as just being some value u, some dummy variable u, in a chain rule application. That cosine of u is, its derivative is negative sine of u, right? So we end up with negative sine of u over here incorporating itself into our result, right? However, we don't want to report our answer in terms of u. We want to report it with that t squared in place of the u in both our results here, or in our answer for the derivative. Remember, that's chain rule. You're Calc 3 students, you should be familiar with that. The second component, well, that's a product of two functions. That's product rule. So it's derivative of the first factor times the second. So the derivative of t is 1 times the second factor is 1 times e to the t, right? Plus the first factor t times the derivative of the second. Well, the derivative of the second factor is, well, the second factor is e to the t. Its derivative is e to the t. All right? So its result is e to the t plus t e to the t from product rule. All right? And then lastly, this third component, its derivative, where does that come from? Well, that's just some fundamental rules of differentiation. The derivative distributes itself across the sum and difference. We use a little constant multiple rule and power rule there, folks. T squared turns into 2t. You bring the power out in front and drop it by a power. 3t just becomes 3. That's a power of 1. Brought out in front times the 3 as a constant multiple is 3. And then t drops to the power of 0, which is just 1. So it's 3 times 1, or just 3. And then this here is a constant. Remember, a constant's derivative is 0. So we end up with 0 here, folks. All right? And that is our third component's derivative. So if we go back and we assemble all this back into the derivative of our vector valued function, all right, we can conclude here. Thus, r bar prime of t is just the vector valued function made up of those derivatives as the components of the vector function, right? Negative 2t sine of t squared is the derivative of the first component of r bar. E to the t plus t e to the t is the derivative for the second component here of r bar. And 2t plus 3 here is the derivative of its third component. Right? That's how we apply derivatives to vector valued functions. It just distributes itself as an operator across the components of the vector, these scalar components, and then that derivative operator applies itself to those scalar components as you did back in calculus when you were applying derivatives to scalar valued functions. Right? Those components are just scalar valued functions. All right? So, folks, that is just the introduction here to derivatives of vector valued functions. I have another video coming up a little later on where we look at some quick application over this, but I want to try to make these short so that you can tackle them without too much haste. So let me stop there for the day, and I will post this up to YouTube, and I'll have another video out for you pretty quick with respect to integration. What follows differentiation? Integration, right? The antiderivative operator. And that's my next video. So I'll be back shortly with that.